What if the graphics card already inside your PC is powerful enough to run local AI, but the software has been telling you otherwise? For years, the standard advice has been simple. If you want to run AI locally, buy NVIDIA. Not because every NVIDIA card is dramatically better than every competitor, but because NVIDIA built the software ecosystem that most AI tools expect. That ecosystem is CUDA. And CUDA has become one of the strongest moats in the technology industry. But two very different projects are now attacking that moat from opposite directions. Vulkan is making today's local models accessible on a much wider range of consumer GPUs. Mojo and the MAX platform are trying to make tomorrow's high performance AI software portable across different chips. So is CUDA finally finished? No. That would make a great headline, but it would be bad technical conclusion. People often talk about CUDA as if it were just a driver. It is much, much more than that. CUDA gives developers a programming model for NVIDIA GPUs, optimized libraries for operations like matrix multiplication, tools for debugging and profiling, and years of examples, documentation, and community knowledge. So, when a machine learning framework needs to perform billions of calculations, NVIDIA does not simply hand it a GPU and wish it luck. Libraries like QBLAS, QDNN, and Cutlass provide highly optimized building blocks. Researchers can spend their time designing models instead of rewriting low-level kernels for every new card. That convenience creates a powerful loop. Developers target CUDA because many AI users own NVIDIA hardware. And then in return, users buy NVIDIA hardware because most developers target CUDA. More customers means more funding for software investment, and better software attracts even more customers. So this is the whole loop. This is why comparing only the raw specifications of two graphic cards can be misleading. A cheaper card might have plenty of compute power and memory, but if the application cannot use it properly, that power is stranded. The problem is not always the silicon. Sometimes the problem is the road leading to it. So to understand the escape from CUDA, separate local AI into a few layers. First, you have the model, the billions of learned parameters stored on your drive. Second, you have an inference engine that loads those parameters and turns your prompt into tokens. Third, that engine needs a compute backend, a way to send work to your CPU, GPU, or another accelerator. CUDA is one backend, but it is not the only one. AMD has HIP and ROCm. Apple has Metal. Intel has its own technologies. And then there is Vulkan, an open cross-platform graphics and compute API supported by a broad range of hardware. This distinction matters because Vulkan and Mojo are not really a single product. They are separate approaches at different layers of the stack. Vulkan is the practical route many people can use today. Mojo is a more ambitious attempt to change how high-performance software is written for many kinds of hardware. So the first route begins with llama.cpp, one of the most important projects in local AI. Its goal is straightforward. Run large language models efficiently with minimal setup across a wide range of hardware. It supports CPUs, CUDA, AMD's HIP backend, Apple Metal, Vulkan, and other targets. The model is commonly distributed in a format called GGUF. For a normal user, the useful part is that one GGUF file can hold a quantized model plus the metadata the runtime needs to load it. Quantization reduces the precision used to store model weights. A full precision model may be far too large for a home computer. A 4-bit or a 5-bit version can use dramatically less memory, usually with some quality trade-off. Think of it like compressing a huge studio recording into a smaller file. It is not mathematically identical to the original, but a good conversion keeps what matters while making the result far more practical. Now, on top of it, you can add Vulkan. So, instead of requiring a CUDA-compatible NVIDIA card, llama.cpp can send compute work through Vulkan to many AMD, Intel, and NVIDIA GPUs. On Linux, open source Mesa drivers can make this especially attractive for AMD hardware. Vulkan can also unlock integrated graphics and older cards that are poorly supported by vendor-specific AI stacks. That does not mean literally every GPU will work or that every supported GPU will be fast. The card still needs a compatible Vulkan implementation. It needs enough usable memory, its driver must support the required features, and the backend must have optimized kernels for the workload. But the change in mindset is enormous. The question is no longer only do I own an NVIDIA card, it becomes which backend can make the best use of the hardware I already own. One more correction is very important over here. Apple Silicon usually uses llama.cpp through Metal, not Vulkan. You will see dramatic benchmark screenshots claiming that Vulkan beats ROCm or that one cheap GPU destroys a more expensive alternative. Treat those results as useful clues, not universal laws. Local language model performance has at least two very different phases. Prompt processing measures how quickly the system reads the context you provide. Token generation measures how quickly it produces the answer. A backend can lead in one phase and lose in the other. Results also change with the model. The quantization level, the context length, the driver version, memory bandwidth, and how many layers fit in VRAM. Even the same graphics card can behave differently on Windows and Linux. Vulkan's greatest advantage today is often compatibility and ease of access, not guaranteed victory in every benchmark. CUDA still has extremely mature libraries, wide framework support, and optimized paths for popular models. If your job depends on PyTorch, training, custom CUDA extensions, or maximum throughput from an NVIDIA data center GPU, switching stacks just to make a point would be foolish. But for a person who wants private chat, document search, coding help, or an offline assistant, the faster theoretical backend may not matter. If Vulkan lets an existing AMD card run a useful context model without buying new hardware, it has already won that user's real benchmark, which is cost. The second route in this whole scenario is more ambitious. Mojo is a programming language created at Modular, the company co-founded by compiler engineer Chris Latner. Latner also started LLVM and created Swift. So this is not a random attempt to put a flame emoji next to Python and call it a revolution. Mojo aims to offer Python-like ergonomics with the control and performance needed for systems programming and GPU kernels. Underneath, it is more on compiler infrastructure designed to target different hardware. Modular's larger platform, MAX, tries to provide a unified AI compute layer. The promise is that developers can build models and kernels without maintaining a completely separate implementation for every vendor. Why is this difficult? Because performance portability is much harder than code portability. A program can technically run on an AMD, an NVIDIA, and an Apple GPU and still perform terribly on two of them. Different chips have different memory systems, execution widths, specialized instructions, and scheduling behavior. Reaching high performance normally requires hardware-specific tuning. So Mojo's bet is that developers can express those low-level differences through reusable abstractions. The compiler can specialize the program for each target while the high-level algorithm stays recognizable. That is a far bigger goal than simply running a quantized chat model on a spare gaming card. It is an attempt to reduce the cost of building and maintaining the AI infrastructure itself. Modular has published examples comparing structured Mojo kernels with NVIDIA's CUDA's library. In one comparison, a Mojo implementation reached equivalent performance for a specific block-scaled operation while using far less operation-specific code. That is impressive, but phrase it carefully. It does not prove that Mojo has beaten CUDA everywhere. CUDA is an entire platform, not one single benchmark. CUDA contains a vast collection of tuned components, and a result on one operation and one GPU cannot represent every single AI workload. The more defensible conclusion is still significant. High-level, reusable abstractions may not require sacrificing peak performance. If that idea holds across more models and more hardware, development teams could stop rewriting the same fundamental operations in CUDA, HIP, Metal, and other languages. A smaller team could support more accelerators, and a new chip could become useful without waiting years for an ecosystem to catch up. That is the real threat to the CUDA mode. Not one benchmark where a bar is slightly taller, but a world where software becomes easier to move. In June 2026, Qualcomm announced an agreement to acquire Modular. The official announcement did not disclose the purchase price, so be careful with headlines presenting a rumored number as confirmed fact. The strategic logic, however, is clear. Qualcomm sells compute hardware across phones, PCs, edge devices, and increasingly data center systems. Great silicon is not enough if developers must rebuild their applications to use it. A portable AI software can make Qualcomm hardware easier to adopt and can reduce the industry's dependence on software controlled by a direct competitor. For modular, Qualcomm brings scale, hardware access, and a path from enormous servers down to devices people carry in their pockets. The optimistic outcome is an open, high performance ecosystem spanning many vendors. The risk is that an acquisition changes priorities or narrows the platform around the buyer's hardware. So, what should you actually do? If you already own an AMD or Intel GPU and want to experiment with the local language models, start with a tool built on llama.cpp. Download a quantized GGUF model that fits in your available memory, confirm that the application is using the Vulkan backend, and compare it with CPU performance. On Apple Silicon, use the metal path. Do not buy a new graphics card until you have tested the workload you care about. A small coding model, an 8 billion parameter assistant, and a huge mixture of experts model have completely different memory and performance requirement. If you are building production training systems or you depend on CUDA only libraries, NVIDIA remains the safe choice today. Ecosystem maturity has real value. If you are a developer interested in the future of portable kernels, watch Mojo and Max, but evaluate what they support now, not only what the roadmap promises. And if your main goal is private, offline inference, remember that useful beats impressive. Model running at a comfortable speed on the hardware you own or already paid for may be a better system than a benchmark champion that needs a completely new PC. So, conclusion, CUDA is not dead, but the assumption that AI must begin and end with CUDA is weakening. Vulkan and llama.cpp are opening more of today's hardware to local inference. Mojo and Max are exploring whether tomorrow's AI kernels can be both portable and fast. These projects attack different parts of the problem, and neither one makes hardware differences disappear. What they do create is choice, and in a market built around lock-in, choice may be the most disruptive benchmark of all. If you want a follow-up where I test the same GGF model across CUDA, let me know in the comments.